So let's start with the definition of continuity. Today's title is Continuity and One-Sided Limits. I forgot to pray today, didn't I? That's all right. So let's start with the definition of continuity. A function is continuous. Continuous. A function is continuous when it has no jumps or holes. That's a simple, not very rigorous definition. No jumps or holes. The more formal definition you can find in your textbook, but I'm personally, not a mathematician. My background is in physics, and so we don't really, as a physicist or engineer, we don't really care about these things like continuity or discontinuity. And so sometimes our definitions are a little more informal based on my personal background. And so for today, no jumps or holes will suffice. Okay, so for example, if we had a function like a parabola, right? A parabola doesn't have any jumps and it doesn't have any holes, so we would say it's continuous at all points. Okay? Continuous. On the other hand, we might have a function like 1 over x. You guys all know what the graph looks like. 1 over x. That graph looks like this, right? It has a vertical asymptote at x equals 0. And so we would say that this graph has a discontinuity at x equals 0. Discontinuous at x equals 0. Right? Because it has a jump between positive x and negative x. Okay? And then the second kind of discontinuity is a hole discontinuity. Or I'll go with this slide. Second kind of discontinuity is a hole discontinuity. So for example, we might have a function like x squared minus 1 over x minus 1. And this is actually a line. What is the line? X plus 1. The line is like this. The graph of this is a line, but there's actually a hole. There's a hole at x equals positive 1. And it's a hole with an open circle, right? We draw it with an open circle because the function is not defined at x equals 1. And why is that? That's because when x equals 1, our denominator is going to be 0, right? And so it's not defined there. But everywhere else, it is defined. And so we would say that this function exhibits a discontinuity at x equals 1 because of that hole. Okay, very easy. Continuity. Now we also typically talk about an interval of discontinuity, okay? It's the second kind of terminology. Basically, an interval of continuity is the set of all x such that the function is continuous at that value of x, right? So if we would go back to these functions, this function is continuous on the interval negative infinity to infinity because it's right continuous at all points. Continuous at all values of x, so it has a interval of continuity negative infinity to infinity, whereas this function would have an interval of continuity at everywhere except 0, right? So we would write this. It's continuous at everywhere except 0. And this function everywhere except 1. So we would write that, the union of these two sets. All right, and the open parentheses, you guys remember? open parentheses means that it's not including 1, but going up to 1. Okay? So that's the interval of continuity. Any questions up to here? Just 2 terms that you guys need to know. Continuity and interval of continuity. All right, the next thing we need to talk about, 2 more terms. There are 2 different kinds of discontinuities. One is called a removable discontinuity, and the other is called a non-removable discontinuity. So, removable versus non-removable discontinuity. Basically, a discontinuity is removable if you can get rid of it really easily without significantly changing the graph or the function itself. Okay, I'll give you one example. Okay, the one that we looked at right before this, what was it? This one? This discontinuity is actually a removable discontinuity, and I'll show you why. The function was f of x equals x squared minus 1 over x minus 1, right? And where is this discontinuous? Very good. At x equals 1, it's discontinuous at x equals 1 because that makes the denominator 0, right? But the reason that we call this a removable discontinuity is because we can actually get rid of it really easily. We can remove it. And the reason is that if we factor this, if we factor the top, right? What does the top factor as? Anybody? Yeah, it's a difference of squares, right? X squared minus 1 squared. So that's x minus 1 times x plus 1. So if we factor the top, and then the bottom stays the same, x minus 1 actually cancels out, right? We're able to cancel these 2 things out. And so that really just leaves us with x plus 1. Which no longer has any discontinuity, right? You're right. X plus 1 is continuous everywhere, and it's just the line that we just graphed. The only difference is that it doesn't have a hole anymore, right? So if I were to graph these two functions, my original graph of x squared minus 1 over x minus 1, that actually has a hole at x equals 1, right? As we found out before. So the graph would look like this. 1, 2, the hole is there. But if we rewrote the function by simply canceling out the denominator, the graph is not quite the same, but very similar, right? It's pretty much the same, except now it doesn't have a hole anymore. So that's why we call it a removable. Hello, this is Jacob. Okay, sure. Take it back. Yeah. To take everything?
Yeah, my mom's here. Sure.
See you. You need a slip? It said to take everything.
Oh, really?
Yeah.
Oh, my mom's here.
Take a slip.
Thank you.
Yeah. Yeah, question?
Pretty much all discontinuities
Are all what kind of discontinuities? Whole. All that I can think of off the top of my head, yeah. I think that's a good rule. Whole discontinuities are removable. Yeah.
The if you can remove it, it's just by factoring.
Yes. If stuff cancels and you can get rid of the denominator and remove it algebraically, then it's a removable discontinuity.
Okay, and then how can you tell if there is a hole by just looking at the equation?
You can only tell that it's a hole after factoring.
Okay.
Yeah, so for example, if it was like x squared plus 1 over x minus 1, this would actually not be a hole anymore. And you can only tell that because this doesn't factor. Okay.
Then how do you tell like that has a hole? Like how do you know
This one?
x squared minus 1 over x plus 1 has a hole?
Yeah, you can only tell after factoring and seeing that things cancel. Yeah. Good question. Anything else? Okay, well, an example of a function that does not have or has a non-removable discontinuity would be something like 1 over x, right? We just saw that earlier. Or let's make it more interesting, 1 over x minus 1, just to make the discontinuity at the same value of x. Okay, so if I were to graph this, right? If I were to graph this, I would have a vertical asymptote at x equals 1, because that makes the denominator 0, right? And then my graph would look like this. And this discontinuity is not a hole anymore. It's a enormous jump. And this is what we call a non-removable discontinuity, because it's not something we can easily get rid of, I guess. Right? This doesn't factor, it doesn't simplify anymore. We can't eliminate the denominator. And so there's really nothing we can do about it. So we call it a non-removable discontinuity. Okay? Any questions? Try to go over more examples later, but we can move on for now. Unless there are questions. Good? Okay. Next thing is one-sided limits. I think we already talked about this during our first lecture, but a one-sided limit is basically we're just approaching the function, approaching the x value just from one side only, okay? And so we write it as, I'll write it big, limit x to, for example, 1, and then we write a small plus sign, kind of like an exponent. And that indicates that we're approaching x from the right side. So if we were to imagine a number line, like here's my 1, this is x, we're simply approaching it from the right side. So this is the limit. This is the limit from the right side, or the positive side. Here, f of x. On the other hand, a limit that's from the left side, we write it using a minus sign, kind of like an exponent to the right above the 1. And that looks like this. X to the 1. Okay? You guys see this? Make it bigger. And as we all learned from the first lecture, the limit only exists. The limit of f of x only exists if the left and right limits are both the same, right? It exists if the limit as x approaches c from the right side, from the positive side, is equal to the limit as x approaches c from the negative side. Okay, so I'll give you guys a quick example. Let's say we had a function looking like this. Let's say here is 1, and then here is maybe 1 and negative 1. Let's say on the left side it looks something like this. And then there's a closed circle here, meaning that f of 1 is 1, right? Because it's closed. It's a closed circle. We're defining it at positive 1. And then we're going to have an open circle, something like that. So this kind of discontinuity we would call a jump discontinuity, most likely non-removable. Okay, so based on this diagram, we would say that the limit of f of x as x approaches c, or 1, right? As x approaches 1 from the right side, this would be negative 1, okay? Right? Because as we approach x equals 1 from the right side, the y value is approaching negative 1. On the other hand, the limit as we approach 1 from the left side is actually positive 1, right? Because as we go from the left side, it's positive 1. And so the left and right limits are defined. But as we all remember, the actual limit does not exist. And the reason is because these limits are not equal to each other. So that's left and right limits. I think it's mostly review. Any questions? Left and right limits. Okay. Final two things are pretty quick, but they're just two more definitions that we need to go through. The first one is continuity on an open / closed interval. So sometimes a function is defined as continuous on an open interval, and sometimes it's defined as continuous on a closed interval. Okay. That's because some functions, right, they're only defined on a certain domain. So they're not defined for all values of x, but maybe only some values of x. Okay. So for example, if we had a function that looks like this, maybe. Let's call this f of x. Let's say this is a and this is b. Then we would say that f of x is continuous on the closed interval a comma b, right? And it's a closed interval because we have those brackets instead of the parentheses, right? So we're indicating that it's continuous also at the endpoints a and b, not just an open parentheses, but the closed brackets. Okay. On the other hand, perhaps we had a different function, maybe like that look like this. Maybe at a, it's like the function is defined here, but it looks more like this. Something like that. And so, the open holes indicate that the function is not defined at that point, but rather at a different kind of point. So here, we would say that the function is not actually continuous at its endpoints. So at its endpoints, both x equals a and x equals b, the function is not actually continuous. There's a discontinuity, even at b, okay? It's discontinuous at the endpoint. And so we would write that the interval of continuity is actually with the open parentheses. Okay, any questions? Pretty standard. Okay, next thing, final thing, is intermediate value theorem. It sounds very complicated, but It's actually very simple. Let me find the more exact statement. If f is continuous on the closed interval a comma b, and f of a is not equal to f of b, then there is at least one number c in a comma b interval such that f of c equals k, where k is some number between f of a and f of b. Sounds very complicated, but it's actually very simple. Huh? Yeah, it sounds complicated. That's what I said, right? But it's very simple once you just think about it, okay? Do I write it down? Okay. I think there's one test question on it. So just know what it is, okay? You don't really need to use it to solve many questions, but just know what it is. Basically, it's very simple. Very, very simple. Let's say I have my coordinates here, x and y. If I have a function that starts at a, it starts at x equals a and ends at x equals b, and let's say ends here, sorry. This is f of b, and this is f of a, right? Okay, and let's say k is just some number in between f of a and f of b. Let's draw a line here. All this theorem is saying is that if this function is continuous, if f is continuous between a and b, all this theorem is saying is that it has to pass through k somehow. That's it. Right? Very trivial, but sounds a little complicated. Right? You get the idea? If it's continuous on this interval, then there has to be at least one number. There has to be at least one number c such that f of c is equal to k, as long as it's continuous between these two points, a and b. Very simple, right?
So we can't like stop and then have
Right.
open dots above it or something.
Yes, the reason is because it's continuous, right? Because if it was not continuous, then we could have something like this. It could look like this, right? Maybe this.
Yeah.
There's some jump, and then it could, pass by. Yeah, it could pass by this k value if there was some discontinuity. But as long as it's continuous, it has to pass through k. It could pass through multiple times, which is why I said at least one, right? We could have something like this. It could pass through 3 times. Can it ever pass through an even amount of times? No, right? Because it has to go through an odd number of times in order to get to the other side. Okay, any questions? Feel free to work on the homework, but please be quiet because I am going to also work on some example problems on the board. So just in case you guys want to follow along if you're confused about anything. But if you think you're totally fine, you can get started on homework. But just don't talk because I'm going to go through some questions up here. Okay. Here are some warm-up questions. They're posted on Moodle if you want to follow along. It's chapter 1.4, warm up. Let's do some good ones. Okay, 2 and 3 are good. It asks us to find the limit of this square root of x minus 1 as we approach from the right side and also from the left side. Okay? So it might help if you graphed this. If we graph this function actually looks like this. If this is x equals 1, it looks like this. And so you can see how it's only defined for x greater than or equal to 1, right? And so if we imagined x kind of getting closer and closer to 1 for this function, we know that eventually this limit is going to equal 0. It's going to equal the square root of 1 minus 1, which is 0. But that's only going from the right side, okay? You can imagine like if x was 1.0001 minus 1, this would still be defined, right? So from the right side, there are no problems. It's from the left side where we encounter problems, right? Because if x is less than 1, right? If we're approaching x equals 1 from the left side, then x has to be less than 1. But the problem if x is less than 1 means that the thing under the square root is going to be negative, right? So we're going to have maybe like 0.9999 minus 1. But this is actually not allowed, right? Because this is the square root of a negative number. This is square root of 0.0001. And so that's not okay. And so this limit from the left side actually does not exist. This would be a DNE. Okay? Any questions? So that's an example of where a limit might fail on one side but be fine on the other side. Next one. Another example. So we have a piecewise function here, meaning that if x is less than or equal to 0, the function is defined as this. If x is greater than 0, the function is defined as this. So if we were to evaluate the limit as f of x approaches 0 from the left side, then we should plug it into here, right? Because x is less than 0. We're going towards 0 from the left side, so x is less than 0. So this condition is satisfied. So we would simply plug in 0 into this, right? Because we're approaching it from the left. So this would be 0 squared plus 1 equals 1. Okay? On the other hand, if we were to approach it from the right side, x would be positive, right? Because we're going towards 0 from the right, and so we're in the positive territory. So here, we would actually plug in x. We would plug in x equals 0 into the second part. So we would have 2 times 0 minus 3 equals negative 3. So negative 3 is the limit of f of x as we approach x from the right side, as we approach 0 from the right side. And so this actual limit does not exist because they're not the same, right? We don't have the same limit going from the left side and the right side. Okay? This is an example of a question asking about discontinuities. The answer is A, x equals 2, because this function is discontinuous whenever the denominator is 0. That's x equals 2. That's it. Skip. Okay, let's do question 7. Use the intermediate value theorem to show that the function has a 0 in the interval 0, 1. So let me evaluate f of 0 first. F of 0 is 3, right? 0 squared minus 7 times 0 plus 1 is 3. But f of 1 is 1 minus 7 plus 3 equals negative 3. And so the question is asking whether it has a 0 in the interval 0, 1. It's basically asking, is there a value of x between 0 and 1 such that f of x is equal to 0, right? And the answer is yes, because if we were to graph this, right? If we were to graph f of x, f of 0 has to be 3, so it's 0, 3, but f of 1 is negative 3. F of 1 is negative 3. And so we know it's continuous, and so in order for it to, right, get to the other point, it has to cross the x-axis between 0 and 1. And so that means it indeed does have a 0 between in the interval 0, 1. Okay? So that's how we actually use intermediate value theorem for a question. Let's find one with, okay, let's do number 10. It's talking about removable versus non-removable discontinuities. Okay? So we know that this is going to have discontinuities because there are going to be values of x such that the denominator is 0. But we don't know yet which ones are removable and which ones are non-removable. In order to do that, we need to actually factor the numerator and denominator. Numerator stays the same, but the denominator we can factor as x minus 2 times x plus 2. Right? It's difference of squares. X squared minus 2 squared. And so when we look at this, we can actually see that there are two discontinuities, right? There's one at x equals 2 and one at x equals negative 2. But the one at x equals 2, right? The one at x equals 2 is removable because we're actually able to cancel these two things out. We're able to cancel this out and write it as 1 over x plus 2. And we can't simplify beyond that anymore, right? So we would say that x equals minus 2 is non-removable because we can't get rid of it by factoring and canceling. But the x equals 2, right, this factor, the x equals 2 is removable because we were able to get rid of it by factoring. Got it? Okay, there's another question on homework that I think it might be a little tricky, so I want to go over it. I think it's the last question. Let me find it. That one's tricky because it asks you whether there's a discontinuity, but the denominator actually does not factor. Let's see. Okay, yeah. The question is, I don't know if it's the exact same values. Maybe it is. That would be bad. The question is to determine what's the interval upon which this function is continuous. And the function is x squared plus 3x plus 7. And it's asking you to find where is this function continuous. Okay, so in order to find where this function is continuous, the typical way is we just want to figure out first, where is it discontinuous? And so we would want to figure out where or for which values of x is the denominator going to equal 0. Okay? And once we're able to solve this, we're able to find where the discontinuities are. Okay? The problem is that this doesn't factor, right? And so we would actually have to use the quadratic formula. Right? Negative b plus or minus, what is it? Negative 3 plus or minus b squared is 9. And then 4ac is minus 28 over 2. And this evaluates to square root of negative 19 over 2. Okay? But when we look at this, right, this is not a real number. It's an imaginary number. It's a complex number. And so therefore, there's actually no value of x. There is no value of x such that this equals 0. And so this denominator is actually always positive. And so therefore we would say that f of x is continuous for all x. And so the interval of continuity is negative infinity to infinity. Audrey?
Is there any way to look that over? Or is this just like?
Let me look at the test. Yeah, I'll check right now. Any other questions?